Now, when working with probability distributions, we have the probability function, we have the probability curve. There's also something known as the cumulative distribution function. The cumulative distribution function, or the CDF, of a random variable is denoted by capital F. This just represents the probability that the random variable is less than or equal to a particular value. So f of x, capital F of x, is equal to the probability that big X is less than or equal to little x. So it's the area under the probability curve, if you have a continuous random variable, to the left of x. Okay? If you have a discrete distribution, then you just count up the probability values for all x less than or equal to a particular value. And you usually get a stair-step kind of function. The cumulative distribution function satisfies the following properties. So if x2 is bigger than x1, then the area to the left of x2 is bigger than the area to the left of x1. The CDF at minus infinity is 0. The area to the left of minus infinity is 0. And the CDF at infinity is equal to 1. So the area to the left of plus infinity has to be equal to 1. This just says the total area under the probability curve is equal to 1. Because the total area under the probability curve is equal to 1, the probability that x is greater than, the random variable is greater than or equal to x is 1 minus the probability that's less than or equal to x. If we want to know the area, or so if we want to know the probability that x is between, that the random variable is between x1 and x2, it's the CDF evaluated at x2 minus the CDF evaluated at x1. So this result here is one of the main reasons why we look at the cumulative distribution function. If we want to know the probability over an interval, we can just calculate the difference between the CDF values. And so if we have some function that can compute the CDF, then we can compute the probabilities. And if we have a continuous random variable, it turns out that the probability curve, the density, is equal to the derivative of the CDF. So there's a result from calculus. And this is just an example of Fabini's theorem. Okay. So let's look at an example. Suppose we have a uniform distribution over 0. Oh, actually, before we go to the uniform distribution, let's just look at, so this discrete distribution for Microsoft stock that we had before. So if we looked at this distribution here, so this is the probability mass function. And if we want to know what is the cumulative distribution, what is the probability that x is less than or equal to 0, well, it's the sum of the probabilities that x is less than 0. So when we calculate the cumulative distribution function, we see the probability that x is less than minus 4 is 0. The probability that the return is less than minus 3 is just the probability that it's equal to minus 30%. So this is the probability that you're in a depression. And then the probability that the return is less than, say, minus 10%, well, again, that's the sum of these two events. And then we just add up the probabilities and we get this stair step. So that's discrete distribution. If we have a continuous distribution, say we have a uniform distribution on 0, 1. So in that case, we have a very simple distribution. So we have a distribution that's essentially the square. That's supposed to be 1. And so we want to know what is the probability that this random variable x is less than or equal to little x. Well, that's the area under the curve to the left of x. So if we think of some value here, x, then this area under the probability curve to the left of x is just the shaded area here, which I'll shade in. And so this represents the probability that x is less than or equal to x. It's just the area under the probability curve to the left of x. And we can do this integration very easily because the probability curve is just equal to 1. This probability is just the integral of dz from 0 to x, and so that's equal to x. So for a uniform distribution on the unit square, if we want to calculate the CDF, it's just a straight line that looks like this. So this is f of x is equal to x is the CDF. So this is the case where we can analytically derive what this CDF is by actually evaluating the integral. And then if we want to find the probability, say that x is between 0 and 1/2, then what is this? This is just the area under the probability curve between 0 and 1/2. We can evaluate the CDF at 1/2 minus the CDF at 0. The CDF at 1/2, using this result, is 1/2. The CDF at 0 is 0, so the area between 0 and 1/2 is equal to 1/2. Okay? And then similarly, the result from calculus, because the CDF is equal to x, if we take the derivative of x, we get 1, and that's exactly the probability curve. So with a continuous random variable, we integrate, we take the derivative of the CDF, we get the probability curve. All right, so I want to make a remark here. So in this example, let's say when we had this, the probability curve on the unit square, right? We can think of the probability, say that this is a probability, say, between 0.5 and 0.6 is the area under the curve. So this is equal to the area under the curve. Okay. So what happens if we consider the probability as this interval gets smaller and smaller and smaller? So the idea is we want to think of what's the probability at a single point. So if we squish this rectangle such that we just get a single point, what's the area associated at a single point? It's 0. So with a continuous random variable, the probability that a continuous random variable is exactly equal to a particular point is 0. Now that's a little counterintuitive, right? Because when you say the probability of x being equal to a particular point is 0, it's like saying it can never happen, right? That's not true. And so it's sort of like with a continuous random variable, again, there's an infinite number of values between 0 and 1, right? And think about the idea of guessing, exactly what x is going to happen, right? You can have as many decimal points after this, of accuracy that you want. So in some respects, probability of a single point for a continuous random variable just doesn't make any sense. And so for continuous random variables, we define probabilities over intervals and not at distinct points. And with a continuous, and because of this result, when you have a continuous random variable, the probability that x is less than or equal to x is the same as the probability that x is strictly less than x, because the probability at a single point is equal to 0.